Before we get started, I did want to learn a little bit about you all. So I want to adjust my language, my discussion as we go through. I think Dr. Deepak already started answering some of these questions, but just hands up right now. Are you a bachelor's student? Bachelor's level students? Master's level students? In the back. Why do master's students always sit in the back? Okay. Doctoral students? Okay. And you guys are on the side too. Any postdocs? And clustered together in the, you guys always postdocs always sit together? Okay, osmosis. It's supposed to work where you like distribute across, not separate. That's an entropy going the wrong way. Okay. And then, okay, go ahead, raise your hands. Okay. Oh, so nice to see you all. So welcome everybody. I will try to adjust the discussion. It does help to know that right now we don't have any bachelor's students, so I can start from a little bit more of an advanced position. And anybody else that I didn't? Okay. So, maybe that first question right there. True? I know that fluorine's important. Okay. I don't know that fluorine's important. Do I need to convince anybody here? You heard in the introductions about 40% of recent approvals are fluorinated. Historically, about 30% of molecules are fluorinated molecules. And why? And the why is what we're going to talk about over the next several days. Who knows about all the different types of fluorinated functional groups that are out there? You've seen an aryl F bond. You've seen an aryl CF3 bond. What are some of the other substructures you're aware of? But the types of substructures themselves, how many do you know beyond CF3 and F, the group? What other types of groups do you know of? Single atom substitution, yeah. So I hope that we can learn some diverse structures and understand where they're relevant and why they might be useful. So that should be a goal. That should be something you keep in mind where we're going as we move forward. So the last one there. Who understands the why? So why does fluorine and fluorination impact all the properties that make it useful for drug discovery? Who understands why? So it's a smaller size, absolutely. Why does that matter? Is it? It's a bioisosteer of hydrogen. What else? So CF3 would be a bioisosteer of CH3. So there are many myths in fluorine chemistry, and we want to avoid using myths to guide our rational design. And so as we go through, we're going to talk about some myths, some lore. We'll explain why those myths and those lores are true as we move forward. But we're also going to dispel myths where they're not true, and we'll come back to some of these things. But there are many whys, and I want to ensure that everybody leaves here understanding the basis for why fluorination works. It's important for several reasons. If you understand the why, you might be able to extrapolate the knowledge and take it to other systems. So if you are dealing with fluorine, you say it's an electron withdrawing group. Okay, what other electron withdrawing groups might modulate a molecule? So you might be able to extrapolate the basic principles outside of fluorine chemistry. So that's one thing to keep in mind. Okay, the second thing is you have to understand why, so you're not just randomly making a bunch of compounds that may or may not solve the problem you're trying to deal with. You only have so much time. You only have 2 hands. You can only run 5 or 6 columns at a time, right? I think I heard that from some students a couple of days ago. Being able to rationally design compounds can save you time in the long run. You can design fewer compounds, address the issues with your molecules more directly if you understand the why. And so that's what we want to do. In order to understand that why, we need to understand the physical chemical properties that are perturbed by fluorine. So as medicinal chemists, as discovery chemists, we're definitely interested in understanding how fluorine perturbs all these physical chemical properties. And when you think about drug discovery, drug design, you're always measuring and checking and testing on all these types of properties. I'm going to use the term DMPK. A related term is ADME, administration, distribution, metabolism, excretion. Everybody's aware of that. And DMPK is related, distribution, metabolism, pharmacokinetics. So if I'm using that terminology, yeah, I've let you know, but if you don't remember it, let me know, and I'll remind you all, okay? So as medicinal chemists, we're using DMPK considerations to select molecules, to promote molecules, and fluorine is going to perturb many of those properties. That's why it's so valuable. But unless you understand the basic physical chemical properties that are being modulated, it's going to be difficult to rationally use these strategies. So again, the goal today in this exact lecture and the tutorial that follows it up will be to focus on really basic principles. So for a little bit, you're going to feel like you're in like an undergraduate or undergraduate course on basic chemistry. And we're really going to focus on fluorine. And then we're going to move forward, start talking about organic fluorine compounds and some of the reactive intermediates that form, and then we'll eventually move into the drug discovery. So it's going to start very basic, but it will move closer and closer and closer to the things that we want to talk about over here, okay? But let's start with some very basic properties first. So in the slides, most of the slides you have are going to be minimal slides. They're going to look like this. And as I talk through things, they're animated. So you're going to see animations pop up that are not in the slides that you were provided earlier on. So do pay attention to the animations. So here is a select series of properties for a select series of atoms. You can see our halogens on top. You can see other first row atoms over here on the bottom. And we just want to draw a comparison between fluorine and some other substructures. Fluorine itself is very hard. It's a small element. We know that from, again, high school chemistry, first semester of your bachelor's chemistry. Very electronegative element, prefers to be anionic and not cationic. Tell me about the size. And so we already started this conversation. Oh, sorry, it's very electronegative there, so that's going to be a key property that we'll be discussing about over and over and over and over. It wants to pull electrons towards itself. So in terms of size, there's fluorine, neutral state, van der Waals radius, a little bit bigger than hydrogen. So in terms of a direct isostere, not true. Let's dispel that myth right away. We're going to continue to dispel it over the course of the day. It is not the same size as hydrogen. We'll look at physical chemical data on organofluorine compounds that supports this argument also. It's actually closer in size to oxygen and nitrogen. So even though many times you can replace a hydrogen atom with fluorine, that just means the receptor, the enzyme, whatever the target is, has a little bit bigger pocket. It allows a little bit bigger of a substituent. Fluorine itself is a larger atom. Bond lengths, really important in medicinal chemistry, because you have your small molecule interaging with a target. How far away does your small molecule get from certain residues, from certain substructures in the biological target? The carbon-fluorine bond is notably longer than a CH bond. So again, let's dispel that myth that CH and CF bonds are the same size, same length. Okay, not true. It might happen that you can make that replacement. The CF bond in reality is closer in size to a CO bond. You see length close to a CC bond, right? So it is a longer bond, 1.4 angstroms there. Keep that in mind as we go through. Again, we'll continue to build on these concepts as we move forward. And so we can also look at the steric parameters. This slide talks about two different types of parameters, the Taft parameters and then the A values. Taft parameters those are used for linear free energy relationships, so everybody's familiar with LFERs. Your Hansch parameters, that would be one set of parameters that you've seen for understanding the electronic properties of substituents in an aryl ring. Taft parameters differentiate steric and electronic properties. And here we're just looking at the Taft steric parameter. and a series of substructures. You can see the R groups listed out there, HFOH, a variety of alkyl groups, and then some fluoroalkyl groups as we move down and down and down. And then on the other side, that second column, A values, that's the axial equatorial equilibrium that you've seen before for cyclohexanes. Typically, bulkier substituents prefer to sit equatorial, right? Nothing new there. Now we're just looking at specific data on how fluorinated molecules behave as opposed to non-fluorinated molecules. So let's go ahead and dig through some of this data and ask the question, how big is fluorine? So based on the Taft parameters there, fluorine is not the same size as hydrogen. It's behaving larger. It's behaving closer to a hydroxyl group in size. So again, that comparison between F and O in size still holds true. Let's look at methyl versus CF3. That's a huge difference there, right? CF3 behaves as a much larger substituent. So again, let me go back one real quick. So on the first one, fluorine versus OH, we're only looking at the Taft parameter there. We don't have the A values on this for the OH. When we look at this data, we can look at both the A value and the Taft steric parameter. Both cases, again, that CF3 is huge. It's big. If you're going to try to take a methyl group and replace it with CF3, you better have some space in that pocket, right, to be able to get it to fit. Or that pocket has to reorganize and open up, or something else has to happen, right? We know enzymes are dynamic, right, that residues can move, and so maybe it can open up and accommodate a larger, greasier substituent, but don't assume that they're the same size. So that CF3 group is actually more like a butyl group in size. So look at the parameters, look at the Taft parameter there. Kind of in between isobutyl and T-butyl in size. Symmetrical shape, it's going to have a shape more like a T-butyl group. Isobutyl, again, different shape, because one side's going to be large, unsymmetrical shape there with the isobutyl, but it's big. And same thing with the A values there, right? You can see the A value between CF3, look at the methyl, up there at 1.17, it's definitely bigger, okay? So it's a big element, it's a greasy element. Don't expect it to behave the same as a methyl group, okay? So again, dispelling myths. Here's another experiment, another set of data point demonstrating that the CF3 group is huge. It's way bigger than methyl. And this is going to be energy associated with rotation around a biaxial bond, right? So you have your biaryl. As you rotate around, you're going to come to a spot where the X group, whatever it is, has to eclipse with this hydrogen in order to spin around. And the energy associated with that is what we're looking at. And the bigger substituents are going to require more energy to push that bulkier substituent past the hydrogen when they're syncoplanar there, okay? So that's another data point demonstrating, again, that the fluorine and the fluorinated substituents are going to be much larger in size. So maybe, again, look at the data very specifically, hydrogen versus fluorine, you see a greater energy there. You see your fluorine, your methyl versus your CF3, again, a big energy difference. Using this type of assay, this type of experiment, the CF3 group is closer to a propyl group in size, definitely bigger than methyl. Okay. So we're starting to get a feel for the size of these elements. Hopefully, right at the beginning of the course, dispelled like one of the common myths that's just not true about fluorine chemistry and organofluorine compounds. Okay. So I'm going to pause. I've been speaking for a few minutes here, and I'm going to ask if there are any questions from anybody on these topics so far. Make sense? We're good? Okay. So we can keep moving forward, and we're going to look at some of the different types of intermediates that organofluorine compounds can perturb. So we've seen cations, we've seen anions, we've seen radicals. We know they exist as reactive intermediates. In some cases, they exist in biological systems. When we think about chemical stability, how these enzymes might be metabolized or decomposed in a physiological system, we're going to be thinking about reactive intermediates. And so that's the goal today, is for this is just to start looking at very basic principles here so that we can build on them in subsequent days. We're not going to do everything. We're not going to get to everything in one day. So again, this is very basic, but we're continuing to build. So fluorine. Fluorine is the row with carbon, oxygen, nitrogen. Carbon, nitrogen, oxygen, fluorine. Sometimes in some of the lecture halls, there's like a periodic table right here I can point at, but not here. So then think about vertically, fluorine, you have your chlorine, bromine, iodine. Molecular size changes drastically as you go from iodine to chlorine. Fluorine to chlorine to bromine to iodine, right? And they change because the orbitals are different energy levels, and they get bigger and bigger and bigger, more diffuse, more diffuse, more diffuse. And it turns out that fluorine is the only one of those elements that hyperconjugates well with carbon-based cations or anions. If you think about chlorine and bromine, those orbitals are too big, too diffuse to overlap well with the carbon-based orbitals. So hyperconjugation is an absolutely essential principle for almost everything we're going to do for the rest of the course. We need to be thinking critically about how lone pairs of fluorines can distribute into, overlap with, and stabilize cationic species, alpha. In addition, we need to think about how anions will not be stable next to fluorine because you have a repulsion of electrons. Right? Fluorine pulls a lot of electron density to it. It has all these extra electrons. It's going to push away. There's going to be a repulsion, a destabilizing interaction there. That is something to consider. So those two properties are going to come up over and over and over. Those are hyperconjugative, positive and negative hyperconjugation. Fluorine does both of it. In addition, we're well aware of inductive effects. Being the most electronegative element, it's going to pull electron density towards it. It's going to pull electron density away from carbon. And as such, it's going to have an effect on cationic or anionic intermediates and the stability of those intermediates. So specifically, that inductive effect will destabilize cations. Here we're trying to pull electron density away from something that's already missing electrons. That's not a favorable interaction. In contrast, the anion stabilization, that's actually a good effect. If we have more electron density here, fluorine is kind of pulling its way. It wants more of that, and so that's a favorable interaction. A really key feature to recognize here is that these two effects, the hyperconjugative effect and the inductive effect, counteract each other. They work against each other. One is stabilizing, the other one is destabilizing. And so fluorine in some cases can help stabilize cationic species, but in other cases it can also disfavor cationic intermediates. And so there's this constant push and pull going on when you think about these reactive intermediates, and we're going to continue to build on that concept. Similarly with anions, you have a destabilizing effect through a hyperconjugative effect, but also a stabilizing effect through the inductive effect. And again, these contrasting effects work against each other, and sometimes we use one to explain another a phenomenon, sometimes we use the other to explain a phenomenon. Okay. So you have to keep them both in mind, that they're both simultaneously present in influencing the reactivity of substructures. So the hyperconjugative effect also is present when fluorine is attached to alkenes and or aromatic rings. So, pretend this might also be an aromatic ring here. You would still have a CsP2F bond. Okay, and we're going to talk about some of those as we move forward also. So the lone pair of electrons through resonance can push down, donate down, and present a full-blown anion. Generate a species like this. It's not a great resonance structure. It is a true resonance structure, right? It is there, it is present. But think about the reactivity. That means we have partially nucleophilic character here. We have partially electrophilic character here. That's what's explained by our resonance structure. And so again, when we think about chemical reactivities, we might be able to exploit that for synthetic organic purposes. When we look at drug metabolism, we're going to talk about this property that fluorine can actually donate electrons into a ring while it's simultaneously pulling electron density out through an inductive effect. They're counteracting effects again. And so let's see, what's next? CF3 group. CF3 is so much more simple. It really is an easy group to think about. There's no hyperconjugation. If you have cations adjacent, that's super destabilizing. Maybe a key number to think about is the electronegativity of CF3. The electronegativity of CF3. Anybody have a guess at that one? Yep, same electronegativity scale. Fluorine is 4. CF3 as a group, it's about 3.5. It's a lot, right? That's a pretty powerful electron withdrawing group. Fluorine wins, that's the most electronegative, but CF3, 3.5 is pretty powerful itself. And as it is so powerful, this can be a very, very strong effect. Show a couple of examples of that in the tutorial. When I start asking you all to give me some information like you guys think about stuff, we'll see some examples of that. But it also, because you have a sigma star orbital in the CF bond, that's a CF3 group, and we're just looking at one of the sigma stars, an anion, vicinal, can actually donate into the CF bond. Okay, so the CF sigma star interacting with a p set of lone pair of electrons can actually be a stabilizing interaction. It can also lead to some degradation products that we'll see. Okay, so keep these in mind. We're going to continue to work with them. Maybe we can start to understand or see some data that we can use the different structures as rationalization for. That didn't come out right, sorry. So let's look at some data that demonstrates these types of intermediates. Okay. So first let's look at a series of pKas. That's fluoroform. You know chloroform. You use chloroform all the time, right? This is the fluorine version of chloroform. Look at that pK of 30. So it's acidic. It's not a normal hydrocarbon. That is acidic because you have this sigma withdrawing effect of fluorine. You have 3 of them building up, they're additive in nature. That's how we rationalize the pKa there. But if we use other perfluorinated hydrocarbons, so this one is like a T-butyl group that's perfluorinated there. Look at that pK. Look how acidic that is, 11. That's super acidic, right? It's like a thiol. Why? And I've suggested in the figure why over on the far side here. When you have that carbanion stabilization, that leads to a more stable anion. The more stable anion, lower pKa, right? pKa is a thermodynamic process, thermodynamic property. More stable anions have lower conjugate acid or conjugate acids with lower pKa's. So you can see that as we simultaneously build in more and more CF3 groups, this effect takes over, and you see this massive decrease in pKa. So it's really easy to deprotonate this guy. Think about the bases that might do that deprotonation. It's not going to take much. Yeah, you can use a stronger base over here to deprotonate fluoroform, right? Now the hyperconjugative effect is unique to fluorine. We said fluorine has orbitals of the same size roughly as carbon, and chlorine and fluorine don't. And you can see that in the trend that I'm going to show here on the bottom. So in the bottom we have fluoroform, chloroform, bromoform, and you can see the differences in pKa. Over here, the orbitals can, when we deprotonate, you would make an anion, and that anion has this repulsive interaction that's destabilizing. In contrast, when you deprotonate chloroform, you don't have this opportunity. So it would be easy to rationalize and say Fluorine is a stronger electron withdrawing group. Its electronegativity is greater. You would initially anticipate that its pKa would be lower than chloroform or bromoform. That's just not true. That's not what the data says. The data says that chloroform and bromoform are actually more stable anions. When you deprotonate, they make more stable anions, even though they're less electronegative. And again, we can rationalize that property by looking at this figure here and recognizing that there's a hyperconjugative effect by the fluorine lone pair donating back and resisting, repulsing against the anion that's formed there. So it's a cool thing. It's a unique thing. Hopefully, as we're moving forward, we're going to be thinking critically about these types of properties. And I just want some very simple systems to show them first. Okay? So I'm going to pause again and see if there's any questions or thoughts. And you're going to have to speak up because the AC is out here. So yeah, speak up loud.
In case of chloroform and bromoform, it's never decreases because of involvement of d orbital or very d.
Yeah, the way I interpret that is that the chlorine still can hyperconjugate back a little bit. It's way, way, way less. But the chlorine orbitals, even though they're bigger and more diffuse, can do a little bit of this. And the bromine, being even bigger and more diffuse, can do even less of it for this hyperconjugative effect. That's the way I would rationalize it. Okay.
The conjugative and hyperconjugative effects, we can actually quantitatively measure using quantum chemical methods. How much is the effect? What is the energy associated with it? How much is the overlap between the lone pair electrons and the sigma and the sigma star on the top? All of those effects can be estimated quantitatively, and comparisons become much easier for information.
Right. So there are, right, quantum calculations that would support many of these types of features. All of these orbital interactions can be replicated with molecular modeling at various levels of theory. Absolutely, you're right. Okay, so one more effect, and this is going to be relevant later, that hyperconjugative effect between an anion and a vicinal fluorine atom can be so powerful that you can actually see molecules fall apart, and you can see that CF3 group totally decompose. And it occurs through a fluoride elimination process that's shown here. If we think about taking this interaction to the extreme, that anion can go ahead and donate into the sigma star and fully break the CF bond. And when that happens, you get to fluorinated alkene type intermediates, and you lose F minus, and that's a pretty stable anion, we all know. And so this is also a process that occurs regularly. There's one drug, trifluridine. I didn't think we have time to cover it because it's a pretty intense mechanism with how it interacts with systems, but it is a beautiful example to study. It's a place where organic arrow pushing meets complex biological systems, DNA biosynthesis, folate pathways. It's a really, really, really nice example. It does take a bit of time to talk through a lot of chemistry before you can even look at the drug. But it's a really beautiful system. Okay. So now we're going to start moving into biologically active molecules and thinking about chemical stability in a biological setting. So this would be a prototypical nucleoside, one that has been made, and a couple that have been made and studied before. Nucleoside-based therapeutics are super important, like antivirals, like one of the most important chemical classes for antivirals. You can see the structure there. You have your base, you have your sugar. Who's studied the decomposition of these, the chemical stability of these? Have you seen this in classes so far? You know that they exist, right? Have you thought about how they decompose? Because the chemical structure encodes everything you need to know about that decomposition pathway. So let's look at the data real quick. We have two compounds. Maybe we'll just look at the data on the left compound first. Let's just focus on the left. Okay. So this compound over here, or the pair of them, has that H versus CF3 over here. If we're doing nucleoside chemistry, we have the 1 position, the 2 position, the 3 position, 4, and then 5 would be the primary hydroxyl. So we're on the same page when I'm talking about 1, 2, 3, 4. So this would be a 3-trifluoromethyl group. The stereochemistry, I have it down for the purposes of teaching. It really wouldn't matter with the properties that I'm going to talk about here. The chemical stability under acidic conditions is drastically different. Look at the half-life, the decomposition for the non-fluorinated versus the CF3 variant of those, right? 20 minutes to 89 hours. Acidic conditions. So what I'm going to do, and then the same thing is true over here. So you can look at the chemical stability, H versus CF3. It's a slight variant. You have that alkene there. Chemical stability both at pH 2 and neutral physiological pH drastically changes as you go from H to CF3. So this is a little in-class exercise. And what we're going to do, like you have your page, right? So you're going to explain to me why. And so what I want to do is give you guys about 2 minutes. I'm going to give you a hint. I'm going to give you another 2 minutes to keep developing your answer, and then we're going to talk through it. Okay? So initially work on your own, but we're going to come back all together as a group and talk through it in just a minute. But there's the problem right there. Explain that. In your slide decks, when I give you guys the slides, and I think they were circulated, you have an extra blank slide. So I've given you a little bit of extra space if you need to work on the slides, if you have those printed or in your iPad. But here you go. And I'm done for a minute. Okay, so tell me, what's the first step of this process. We're going to talk about mechanism because we're organic chemists first and foremost, or I am. So what mechanism is this going to go by? It's acid stability. I'm going to wait. This is going to be weird until somebody talks. I can wait a long time. So in the presence of acid, what's going to happen here? Acid-base reaction, right? So where are we going to protonate? Where's our most basic position is going to be over here on the heterocycle, right? We might think about protonating a basic heteroatom on that heterocycle. So maybe we might want to think about a structure that looks like that as the first step. You might be able to think about other spots on the heterocycle there. Oops, I actually changed the heterocycle miraculously. Sorry, when I made my other figure. That was my mistake. Then what? What happens next? There's a key reactive intermediate. Do we have any glycochemists here? Sugar chemists? No, not exactly. Okay, so this is fundamental glycochemistry right here. You have a leaving group. Think of this big thing. What if we just said this entire thing is Lg, a leaving group? Then what do you expect? What if it's a chloride? What would you expect? Maybe we might want to think about a vicinal heteroatom that has lone pair of electrons. And if we borrow the electrons from oxygen to push off our leaving group at the alpha position, we make that intermediate. Now we have an oxocarbenium ion, right? We have a double bond right there. Letting people think. I'm deliberately pausing, letting people think. I see you pointing and talking to your friend. Okay, so if we have the fluorinated functional group X, how would that perturb the stability of the cationic intermediate? That oxocarbenium ion is a structure for which we put the formal positive charge on oxygen. But is that the site where nucleophiles will react? Do they react on oxygen? They react at carbon. So even though we think about an oxocarbenium ion as having a formal positive charge here, this looks more like a carbonyl structure, doesn't it? It's like, think about it like a carbonyl with a Lewis acid or something coordinated. You would still react that at the carbon atom, and you have the same thing here. Instead of a Lewis acid, you have a carbon-carbon bond, but our oxocarbenium is intrinsically electrophilic on carbon. And now let's think about how the fluorinated substructure perturbs the stability of that oxocarbenium ion. And so that oxocarbenium ion would have a sigma withdrawing group. If it's fluorine, if it's a CF3 group, we would be pulling electron density away, making delta plus character over here, but we already have delta plus on the molecule. We have an electron deficient species. We're trying to pull more and more and more electron density away from it, and that's a destabilizing interaction. And that explains this data that's shown up above. If we have H, we can go through this protonation and the formation of the oxocarbenium ion. That occurs really easy for H. But you put that fluorinated group on there, and it's much more difficult. And hopefully you're seeing why we need to think about analyzing, why we need to use those reactive intermediates, understand the perturbations, the sigma withdrawing effects, and some of the other effects as we move forward. Okay, so the CF3 group would destabilize the cationic intermediate. Make sense? It's a powerful effect, isn't it? That's crazy. So, part 2, this one's going to be a little bit quicker. I'm going to give you just maybe 2 minutes to work on this. You can talk with your friend. How would you compare those two on the bottom? You can see the placement C2 versus C3 of the nucleoside. And go ahead and work on that one for just a minute, all right? Okay, we got it figured out? So first I'm going to ask, everybody has to vote. If you don't vote, no tea at the break, okay? So you have to vote. So we have two structures. I'm going to point at this one and then point to that one. Who thinks this one is more stable towards acid? Hands have to come up. This one more stable? This one? I don't see enough hands. There's a lot of people who aren't getting tea. And it might be tomorrow too. I'm a parent. I can be pretty tough. Okay, so let's do this again. I want to see more votes, okay? So this one. So I think group thought a couple more hands came up. So people are still not voting. It's your right. You have to vote. Okay, so is that a joke? Okay. So here we have our two structures. I would be voting for this one. I know the secret. Some of you know it too, apparently. So we need to think about the power of the inductive effect. And is it more powerful when it's closer to the cation or further from the cation? And that's the principle that we're looking at here. So again, we'll be making the cation. We'll be forming the cation here at this position. On one structure, the CF3 will be 1 CC bond away. On the other structure, that would be 2 CC bonds away. And so it's a more powerful electron withdrawing effect when you're closer to the cationic center. So this one will be substantially more stable than this. Again, the bases are slightly different on these structures, but you'd expect this to be outrageously stable. And there are actually some FDA-approved drugs that do have a CF3 group at that position. Sofosbuvir would be one of them. Sovaldi is the trade name, and that was approved, I think, in 2015 for hepatitis. Has a methyl group and a CF3 group, both at that position right there. Okay. So chemical stability, acid stability impacts drug discovery. Why? So where would a drug experience pH 2? GI tract, right? You take an oral medicine, acidic in the stomach, neutralizes as you go further down the GI tract, but initially that stomach acid can decompose. We can stabilize it chemically. There are pharmaceutical strategies for stabilizing compounds, avoiding specific pills formulations that don't degrade at pH 2. They'll degrade at more neutral pHs, right? We have some special coatings and things like that. How else can we avoid stomach acid? Huh? Yeah, so if we use some type of a sub-Q or an IV injection, we can avoid the GI tract. There's certainly plenty of drugs that will inject when needed. Not always the easiest for certain types of patients, but certainly something we can do when needed, okay? But there might be strategies to use fluorine to avoid these acid-sensitive moieties. Okay? So let me pause again. Any other thoughts or comments or questions here? Let's move into some other cool properties. Oh, yeah, sure.
It would be actually quite fun. Instead of CF3, the one on the right-hand side, that is much more stable towards acid. To replace CF3 with fluorine, let's say, things will be altered, right? Then the hyperconjugation might take the front seat as compared to the inductive effect.
Can I use this too?
Yeah.
Is that okay?
It's a hypothetically answer.
Yeah, so
if the structure doesn't exist, or I don't know.
So we'll be looking at this, and you're saying, what if you have fluorine there? So if you have, so I would argue that this is also going to be I was looking for a laser pointer, but I'm on a chalkboard, so I can't point at this. So I would also argue that this will not hyperconjugate.
No.
So it's one too many positions, right? If you had fluorine, where did I put my chalk? Oh, it rolled back. Okay. So if you had, fluorine here, then we could think about hyperconjugation in, but being one position over. So being one position over, we only get the inductive effect. So.
But the unsaturation one over there.
Oh, the unsaturated one might be different. Yeah, so that could probably.
Use extended hyperconjugation.
Yep. So if you had, right, this, then it depends on which position it is, right? So if you had fluorine here, then you could hyperconjugate in, and that would be stabilizing.
Yes.
But if you put fluorine here at the 2 position, destabilizing because it's inductive still.
That would be a dramatic increase from when x equals to h, that is less than a minute. That might actually go.
Yeah, this one, right? This one, if you had fluorine there, would probably be difficult to isolate, purify on a silica column, right? Yep. So that's another good example to think about for sure. Think about your arrow pushing with organofluorine compounds. Think about those hyperconjugative effects. The positioning of that fluorine atom does matter. Yep, absolutely. Okay. So we're going to talk about a couple more properties of fluorinated compounds. And so another important property is solubility. And so this is a really beautiful system. This is a system in which you have water, some lipid hydrocarbon, octane, hexane, maybe your sep funnel, and you have a fluorocarbon. And it turns out that you get a triphasic mixture. So the fluorocarbon hates water and it hates octane, hexane. Does its own thing, totally. And it's dense. So this hydrocarbon is very dense. It doesn't like water. It doesn't like the hydrocarbon. It does its own thing. And maybe we can understand why when we think about really basic intermolecular interactions and the structure of these fluorinated compounds. The representative example we're looking at, it's here. It's an octane per fluorooctane. The properties we're going to talk about are true for many different types of fluorinated compounds. Oh, sorry, that's a hexane. My bad. So it's a fluorinated hexane. So the fluorocarbons have terrible water solubility. And it goes back to some very basic principles of fluorine and the electronic structure. Let's think about the scaffold. The fluorine atoms being so electronegative are pulling a lot of electron density away from the carbon. And that leaves the carbon all across the molecule. All the carbon atoms are highly cationic. and the fluorine atoms are anionic. So it gives you this type of structure in which you have extra electron density. It's kind of shown by electrons. I'm trying to show just extra electron density on the shell of the molecule and cationic character in throughout the middle. Okay, and that has high chemical stability, as we saw earlier. Now those fluorine atoms, they have extra density. How do fluorine atoms hold the electrons in their lone pair of electrons? Are they good at releasing the electrons out? Or the electronegativity makes them want to retain those electrons close? And the second is true. So fluorine, being so electronegative, pulls its electrons towards itself. When it pulls electrons towards itself, they become less basic. So fluorine, when you have a lone pair of electrons on fluorine, those are not very good bases for hydrogen bonding interactions. Okay, now what I'm saying is extremely true for intermolecular interactions. There'll be a different story when we start talking about intramolecular interactions. So fluorine can do intramolecular hydrogen bonding, and we're going to show several examples where that's important. But for intermolecular hydrogen bonds, fluorine is very poor as serving as a base in those interactions. So we can look at this figure again, the schematic on the bottom. Here's our representative fluorocarbon, again trying to show the fluorine atoms on the outside that have the extra electron density, but they don't want to share their electrons. They don't want to engage in hydrogen bonding interactions, so they are not good at hydrogen bonding with water. And that's the predominant driver of water solubility. For something to be soluble in water, even if it's a drug molecule, for something to be soluble in water, it's hydrogen bonding with water that solubilizes it. Okay? So fluorous compounds, really bad at these types of interactions. They're biphasic when mixed with water, and that's what's going on here. The aqueous and the fluorocarbon layers are separate. Now, when you think about the hydrocarbon layer, maybe you might think, gosh, why doesn't it dissolve in hydrocarbons? And well, let's think about why hydrocarbons exist as solvents. They certainly have lower boiling points than things with a lot of hydrogen bonds, but we still have these London dispersion forces, these transient dipoles that exist in the hydrocarbon just because the electrons are migrating around and they happen to kind of drift over to one side. Oh, now we have a little bit of carbocationic character over on this side. And so these London dispersion forces are very important. Intermolecular interactions in hydrocarbons, but those do not exist for fluorocarbons. In fluorocarbons, the fluorine atoms are holding on to the electron density so tight, and those fluorine atoms are so hard, that you do not get this random London dispersion force type distribution of electrons. Those electrons really do stay tightly associated with the fluorine atoms, so while the hydrocarbon might have these transient dipoles, the poor polarizability of fluorine and the carbon-fluorine bonds means that they don't respond. They don't similarly make these transient dipoles, and so you actually get very poor intermolecular interactions between fluorocarbons and hydrocarbons. And that's the reason why these fluorocarbons don't mix with hydrocarbons particularly well either. Okay? So it's a cool phenomenon. It's unique. But recognize that many of these carbon-fluorine bonds do not engage with water. That's going to be really important, again, as we move forward in a couple of days, really Wednesday. So let's look at a couple of other properties here. Maybe the first property, I pointed it out already, but we can recognize it quantitatively on this side is thinking about the density. And so for this comparison, we have our hexane. We have a partially fluorinated hexane. So 111, 222, 33 fluorinated hexane, and then there's perfluorohexane over here. Look at the density of those, pretty drastic. Water, 1.0, the number we all know. So the hexane itself, not very dense, high density. And there's a lot of mass there. The fluorine is heavier than hydrogen, so per unit, yeah, you would expect that to be more dense. That makes sense, right? Okay. So another really cool feature, unique feature of these fluorinated compounds is that they're really light, but low boiling points. Look at that series. Boiling point of 57, hexane about 70. Why is that? Most people, when we think about boiling points, we think about a couple of things, like hydrogen bonding interactions, like water, right? Of course, that's something we think about. But we also think about molecular weight, right? So it'd be easy to start to say, oh, it must be a molecular weight thing. And it's obviously not in this case when you look at the weights there, right? 338 versus 86. That doesn't correlate. Okay. So we've dispelled one rationale for why compounds are typically higher boiling or lower boiling than others. Maybe another thought might be, well, maybe it's the dielectric constant. If you have something more polar, those molecules might, engage in, and that's not true in this case. So again, the fluorocarbons have very low polarizability. The dielectric constant, like these are less polar than hexane. Look at those numbers. That's crazy. It's cool the way that compound 2 is polarized, like almost 6. That's nerdy cool, right? So you have the CF3s there and the CF2s. They're pulling electron density to the left. Over here with the CHs, they're allowing the electron density to go over towards the perfluorinated side, so you get this dipole. So that's a pretty cool feature there. So that has a good dielectric constant. And so ultimately, how do we explain this? We have to think about the intermolecular interactions again. And how strong are the intermolecular interactions between the perfluorinated carbon when it engages another perfluorinated carbon? And what you end up having is this repulsion almost. So again, we talked about this electronic structure in which the CF bonds pull electron density away from the carbon. You have this anionic kind of shell around the molecule, and those, when they engage each other, don't engage very well. There's a bit of repulsion there, and that's why you see this low boiling point. The solvent doesn't want to stick together. It wants to allow itself to go different directions, okay? So moral of the story here, these fluorocarbons don't like much. That's why, one of the reasons why we use them on all types of materials. If you have waterproof jackets or bags or non-stick pans, you put a fluorocarbon on it, nothing sticks to it, right? That's why they're so easy to clean. That's why, if you spray your hiking boots with them, water doesn't get through. Water hates fluorinated carbons. Now, we've done that in society at the detriment to ourselves for health reasons, right? PFAS can build up in tissues and they're toxic. The environment, we're finding a lot of environmental pollution, but they do work chemically for a lot of purposes, for better or for worse. Maybe we can start to understand the whys those work, even outside of medchem. So with that, I think this session I'm going to put on a pause. The next session that we have is going to be a lot more problem solving. So when we had some of those in-class exercises, we're going to do quite a few more of those. And we're going to come back, we're going to keep teaching and teach at a deeper level all of these things. So when we come back, when we reset, I don't know how long of a break we're going to have, but we will be ready to be thinking, be ready to working on your own, and then we'll have some little small group work too, okay? So we'll see you all in a little bit after the break, but I'm not sure exactly how long that's going to be. So we can take a short break for a few minutes and then come back and introduce the tutorial.
Yeah, so I think it was very wonderful. I'm sorry we should have had some of these things. We shared this information with them yesterday, but yeah, so I think we are going to get these things printed now, and so I think in the next class onwards, all your material will be printed so that they have something to write notes and work on those exam. Okay, so we will take around 15 minutes.
15 minutes, so that's 11:20. Come back 11:20?
Yes, 11:20.